Hello, welcome back. In the previous video, we have defined three different techniques for memory allocation: fixed partition, dynamic partition, then segmentation. Every partition has its own advantage and disadvantage, but none of them partition solve the problem of external fragmentation, but paging can. So what is paging and how it allot the memory? Suppose there will be a process which requires 64 KB, okay, 64, okay. So what will physical virtual memory do? It will divide the memory needed for the process into equal parts. Here it will divide 64 bits into 4 different parts, each of 16, okay. And what happened? The OS also divide the physical memory into equal part of the same size. So OS suppose has a physical memory of 120 bytes. So it's also divide it into a 16 KB of equal sizes. Okay. So what will happen? Here each pages get mapped to a physical pages with the help of page table. Okay. So what will happen? A process has a virtual memory which will be divided into a equal sizes, and that equal sizes, each one of them is called pages. Here each one of them is called pages. Okay. Similarly, OS divide the physical memory into a equal sizes, and each of them is called page frame. Page frame. And how we map? We map with the help of page table. Here 0 is mapped with 2. So we map 0 to the 2. 1 is mapped with 3. 3. 2 is mapped with 5. 5. 3 is mapped with 7. 7. Here this will happen. So how do this mapping happen? This mapping happen with the help of bits. How? Suppose you have a memory of 64 bits. Okay. So how many bits you require? You require 2 to the power 6 into is equal to 64. So here you require 64. So suppose you want 20 byte to be converted into physical memory. So first you write 20 byte into bits. You will write, and it will be 01 01 00. Okay. Okay. And you divide the whole physical virtual memory or physical memory into 16 KB. So what is the requirement of each one of them? 4 bits. So if you see, the first 4 bit will tell you the offset number, and last 2 bit tell the page number. So if you see in the virtual memory, 20 come into the page 1, which is tell by the last 2 bit, and what is the offset value? It is a 4, and if you go to the virtual memory, 16 plus 4 is equal to 20. So if I wanted to convert this bit into the physical memory bits, you have to use the page table, and here the 1 is converted into 4. So what will you do? You take virtual memory bits, which is okay. This is offset. Okay. You will not change offset. Okay. You will not change offset. Okay. Offset will not change. And here the physical memory is 120 bits. So it requires 2 to the power 7. 120 is 7. Okay. So you convert 10 into 3 form, because 4 is for offset. So you need 3. Here with help of page table you get 1 is converted into 3. So 3 can be written in 0 1 1. Now this is your physical address. So how the physical address is made? You first write virtual address into bits. Okay. You count. You know the number of bits required for one of the page. Okay. That is 4. So first 4 is for offset. Remaining 1 is for pages. From this you go to page table. Know the page frame. Okay. You come and have a offset value and concrete with it page frame, and this is your physical address. So how will you convert the virtual address into physical address? I hope you will know it. But there is a one big problem here. What is the problem? Here the problem is of performance. Problem of performance. Why the problem of performance occur? Suppose you have a virtual address, okay, here, okay. You have to first divide it into a pages and offset, okay, okay. Then you have to go to the page table, okay. Find the value of page frame, okay. Then you have to concrete this too. This is very time consuming, so your performance get decreases. So how to solve this? You can solve this problem with the help of TLB, that is called translation look-aside buffer. Translation look-aside buffer. What is translation look-aside buffer? It is a hardware cache. It is a hardware cache, okay. What is the work of this hardware cache? It stores the information of each of the KB. So if you have 64 bits, okay, so it store each of the bits and their corresponding physical number. So it is stored like this. TLB have like this: 0 it's physical, 1 it's physical, 2 it's physical. How it will store it? Let's discuss about it. So what will happen? Suppose your CPU needed process 120 bytes, okay. So what will happen? You first go CPU needed it, okay. You go to the virtual table, okay. Then you go to the TLB. If TLB have the data of 20 bytes, then it will give you the directly the physical address of it, to the CPU, and CPU can execute it, and it is very fast because you do not have to configure the thing, do nothing the thing. So it is almost 100 times faster than the finding or using the paging technique. But if the TLB does not have this information, what will happen? Then it goes for paging, just like I told you. But before giving information to CPU, it also get and store in the TLB. So next time, if the same information is required by CPU, then TLB directly give it. So I hope you understand. TLB is a hardware cache. It just store the paging detail to him, and if the CPU next time needed it, so the TLB can directly give it to, rather than again finding it. I hope you understand the purpose of TLB. And TLB has two different terms, that is called TLB hit and TLB miss. I hope you understand it. Suppose the CPU once again require the data of 20 bytes, okay. So what will happen? TLB have it this data, so then it is called TLB hit, and TLB directly give it to the data. But suppose the TLB does not have the information of 21st byte, so what will happen? TLB miss. Then what will happen? TLB paging will find the data and store it to the TLB and give it to the CPU. The next time when 21 bytes data is required, TLB again go. CPU again go to TLB first, ask the TLB. This time TLB hit and directly give the CPU. But there is a one big problem in TLB also. I hope you understand it. If you know, then I will give you hint. TLB have only two information. What? This is a virtual memory, this is a physical memory. TLB have an information of just like 10 bytes, its corresponding address like 100 bytes. Okay. But CPU simultaneously sorry, but in any laptop or in any system, there are many processes running. It does not happen there will be one process. Suppose there will be a two process 1 and process 2. First process 1 is running in the CPU, okay. TLB save the data 10 bytes and 100 bytes. 100 bytes in the physical memory. Okay. Now this process require IO operation. So what will happen? Context switching happen. I hope you know till this what is context switching. Context switching happen and process 2 come. Now suppose process 2 require same 10 byte of its data, because process 1 also require suppose 16 KB data, process 2 require 32 KB data. So they both have the 10th byte. Suppose the CPU require the 10th byte detail of process 2. What will happen? CPU give the detail of the first byte, or it get confused because the second byte is stored in 70. Because no two process can get the same physical data. Process 1 will be saved here, process 2 will be saved here. No two process will have the same physical address. I hope you know this. So this will be a very great problem, because now CPU get confused which one to give, process 1 or process 2 data, because both have the same. To solve this problem, there are two different methods. Okay, first one is not used, but you must know this. First method is that whenever context switch happen, delete the TLB, and again make new TLB for new process. So next time when context switch happen, delete this TLB and again make TLB for new process. But this is very time consuming. Please do not use it. No OS do not use this method. So which method OS use? OS use new method, that is called, instead of saving TLB, the two information, virtual memory address, physical memory address, save one more information, ASID. It is called address space ID. So what will happen? Two virtual memory like this, one has 1, one has 2. So by this address, TLB know that this is then for process 1, this is for process 2. So I hope now you get clear about everything. The next concept is why we use paging. Paging has every advantage, just like segmentation, dynamic programming. Then why we use paging? Paging is used for because it also not have external fragmentation. Why it does not have external fragmentation? Suppose a process come, okay, it requires 64 KB and it is divided into 16 KB. External fragmentation happen. Why happen? Suppose this is OS, okay, here 2 KB, here it is allotted, here 10 KB, here it is allotted, here 8 KB. So it has total 20 KB, but it cannot allot 16 KB. That is why external fragmentation happens. But in paging, everything is divided in equal number. Here it is divided into 16, so here it is also divided into 16. So if anything is required and if it is present, then it must be allotted, because there will be no here also 16 KB, here also 16 KB. OS always divide virtual memory and physical memory in equal sizes, so there will be no chances of having any external fragmentation. I hope by this you will be clear why paging is very important and why OS use paging. By this we will end this video of paging. I hope every doubt of paging will be clear to you. We will meet in next video.